Hello, this is my Lab 6 report for Physics 2212. So, the purpose of this lab was to observe a real-life and simulated model of a bar magnet falling through a conductive tube of aluminum foil. And to do so, multiple key concepts will be used. And the first concept is the BSR law, which calculates the magnetic field given a charge, a velocity, and a distance. And the second concept is magnetic flux, which is the component of a magnetic field passing through a surface. The third concept is Faraday's law, which calculates the electromotive force. And based on the negative derivative of magnetic flux with respect to time. And the fourth concept is Ohm's law, which relates current to voltage and resistance. And final key concept used in the lab is Lorentz force, which can be determined using a current length and a magnetic field. Through the use of all of these concepts, we're able to analyze the behavior of a bar magnet falling through a conductive tube of aluminum foil. And in the real life model, the average time that the bar magnet stays in the tube was 1.058 seconds, and the simulated model for the time for the magnet to stay in the tube was 0.489 seconds. So for the real life model, we used a bar magnet and a long tube wrapped with aluminum foil, and this is the picture of it. And the tube had an inner radius of roughly 1.5 centimeter and an outer radius of 2 centimeter. For each trial of the experiment, I held the bar magnet over the tube and started recording the video released. The magnet and the end footage once the magnet left the tube. And we did this for 5 trials and analyzed the video to calculate the average time that the magnet stayed in the tube, and the average time was 1.085 seconds. So this is the simulated model, and it's a virtual model of the real life system. So first I set the initial condition and constants, some of which use measure properties of the real magnet and tube. And next I coded a function that will return the magnetic field strength given a dipole and a distance. Then I coded a function that would calculate magnetic flux and using a magnetic object and a ring object. Next, I coded a loop that would update the forces on the bar magnet and tube, and that would update the location of the magnet based on these forces. So by running the code, the 3D model is displayed and showing the magnet move down the tube. The time that the magnet stays in the tube was about 0.89 seconds, and by observing the simulation, some details can be found near the magnet in the tube. Are red and blue colors shown to represent the magnitude of the induced current flowing through the ring. The blue color represents counterclockwise current, and the red color represents clockwise current. Faraday's law can be used to determine this using the fact that the magnetic flux on the ring by the magnet points up and that the flux decreases for ring above the magnet and increases for ring below the magnet. And if I were to flip the magnet around, the blue color will represent a clockwise current and the red color will represent a counterclockwise current, since the magnetic flux will be flipped for both situations. The total time spent in the tube in the real world is about twice as long as the time spent in the tube. for the simulation, and this could suggest that some error exists in the experiment, such as the magnet's dipole moment being incorrectly measured, or extra forces acting on the magnet in the real world, such as drag by the 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 drag and also the air resistance. So, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change using Ohm's law if the resistivity in the conductor was almost zero? The current would have to increase drastically. This change would greatly increase the magnetic force on the bar magnet. And what if the holes or slots were cut into the tube? How would this affect the ring current in your model? Cutting holes into the tube would affect the induced ring current that allow for the magnetic force in the system, and the magnetic force would decrease. And if holes are symmetric, the magnet may rotate as it falls.